COVID protocols, primarily due to spacing. I had hoped that everything was going to be back to regular classes and labs, the old normal, because everybody has to be vaccinated. But apparently there are still spacing protocols that have to be met. So they're now tweaking how things are going to go. As soon as that list is out, I'm going to go over with you what I'm looking for in regards to registration for the spring semester. Also, as I chatted with you before, I want you to register to graduate for this May, and I want you to do it before the 15th of May. I'm also going to have you fill out and submit back to me the completed and signed plan of study, and they use that as a graduation audit tool. And I will go over that with you the same time we're going over classes and everything. I think I mentioned last Wednesday that the schedule for the winter session is out. Everything that's being offered is online. It's not L1, and it's not in person. Everything is online. There aren't too many technical courses that you could use, but there are a lot of other courses that you could use to round out your plan of study, particularly if you did not take technical writing, speech, that type of thing early on. You can get that resolved over the winter before you go into the spring. I'm hoping that the spring semester will be out by Wednesday, hopefully before then. If I find out when it's out, I'll send you a broadcast email just so that you'll know that it's out. There's several issues that they also have to resolve. There's a large number of you in the thermal sciences lab, so it's a question of are they going to make 2 labs or how they're going to handle that. They have a number of other things they've been working on for a while. I've asked you before, for those of you that had registered for ANS as student members a year ago, you're getting renewal notices now. So I've asked you, if you register or you continue on with your registration with ANS, and I strongly encourage you to do that, the cost is $35. And if you send me your receipt, I will make sure you get that money back in a stipend check. So far, I've only had 3 of you do that. I had Kara do it last month. Sir and Theodore have done it currently. So they will get their reimbursement in the November stipend. If there are others of you that still want to do that, make sure you get that back to me by at least this coming Monday. All I need is a receipt to show that you have paid it, and then I will reimburse you for that. I guess that's it for general information right now. Okay. Looks like we have everybody. So first thing I'd like to do is go over any type of review you would like to do for the exam on nuclear material science on Wednesday. It'll be in class. I made up the rough draft over the weekend of what I'm going to have for the exam. I'm going to fine tune it today. We start on Wednesday. I will probably lecture for maybe half hour, maybe up to 45 minutes to an hour, and then give you the rest of the time for the exam. It's essentially on torque, but it could also include anything that we've already learned so far in nuclear material science. So this is sort of your time. Anything you'd like to review? Any questions on anything to do with nuclear material science? Everybody feels comfortable with torque then, so I don't need to do a review.
Can we go over a just like a generic free body diagram using 3 different materials and a torque as like where all the cuts are made? And
okay, Ty, since you mentioned it, let's do that. So we use 3 different materials. Okay. I'll ask you to give me which 3 materials you'd like these to be.
hang on. Well, I guess we'll use our classic aluminum 1100. It seems like that on all of them. Aluminum 2014, and aluminum 6061.
Okay. I'm going to arbitrarily pick some links on this. Do you want these to all be solid? Do you want any of them to be hollow pipes?
Well, for what I'm looking for, it doesn't really matter. I'm just looking for the free body diagram portion of it. The calculations I have, I feel comfortable with.
Okay, all right. So let's apply a torque here on the end of 8,000 Newton meters. Torque here of 4,000 Newton meters. Torque here of 6,000 Newton meters. And I asked you to draw a complete free body diagram. Okay. So we draw the member. Okay. We then sketch in or add any forces, moments, torques, couples. Okay. So we have the 8,000. We have 4,000. We have 6,000. That's all that we were given. So we now look for attachment points. We only have one, which is here at the wall. And we know we can only add forces, moments, torques, couples using the equilibrium equations to establish equilibrium. So we know we have three force equations. We have sum of forces in the x direction equals 0, sum of forces in the y direction is equal to 0, sum of forces in the z direction is equal to 0. We have no forces, so all of these are automatically satisfied. We also have the three moment equations. We know sum of moments around the x-axis has to equal 0. Likewise for y. Likewise for z. When we look at these are all making this system want to rotate in this direction. So this is around the x-axis. So these two are satisfied. This is the one that we have to be concerned about. So we know the sum of moments around the x-axis has to equal to 0, and in particularly the clockwise have to equal the counterclockwise. So in looking at this, if we establish clockwise and counterclockwise, we can just arbitrarily start at the end and work back. So this is counterclockwise for 8,000 Newton meters. This guy is clockwise for 4,000 Newton meters. This guy is 6,000. So we know that 14,000 is not equal to 4,000. So in order to put this in equilibrium, we have to add a 10,000 Newton meter clockwise torque here. And then when you finish that, you can just go back and check to yourself. 10,000 plus 4,000 is 14,000 Newton meters going clockwise. 6,000 and 8,000 is 14,000 Newton meters going counterclockwise. So the clockwise equal the counterclockwise. So this is a complete free body diagram for this system. When you go to look at safety, we know that torque only creates shear stress. So, in order to look at safety, because we have three regions, we'll have to do three free body diagrams to see what is going on within this region. Let me do a little erasing here. So if we're looking to see what's going on in region 1, we want to cut it anywhere just to the right of that intersection, just to the left of this intersection. And if we sketch this looking at the left-hand side, okay. Just moments for question? Somebody have a question? Okay.
No, your video just stopped for a second. Now you're back.
Okay. So we're going to sketch in what we have, which is 10,000 Newton meters. We have one attachment point, so we can only add forces, moments, torques there to put it into equilibrium. And again, this is summation around the x-axis. So hopefully you can see we have to have 10,000 Newton meters there. So if we're looking at safety, we know that the shear stress that is created is equal to, in region 1, the torque in region 1 times the maximum value of the radius, because that's where the maximum value will occur, which is on the circumference of this section. And we're going to divide that by the polar moment of inertia for that section. Whatever this value comes out to be, we're going to compare to the yield value for the material that this is made of. If this is greater than this, it fails. If this is less than this, it's safe. Whether this survives or it's unsafe, whenever I give you a quiz and an exam, I want you to examine each section, just in case you make a math error here and you say, it's unsafe, when it's really safe, and then you don't do the rest of it, then you haven't done whatever the quiz or exam is. Any questions on that? If we go to look at the second region, safety, what I'm going to do is I'm going to cut it anywhere for region 2, just to the right of there, just to the left of there, and I'm going to do a free body diagram for that left-hand side. So if I do that, this is the left-hand side. I'm going to sketch in any given forces, moments, torques, couples that exist. We have this guy for 10,000 on the end. We have this guy for 6,000 here. That's all we have that's given for this left-hand side. I can then do, realizing that we have one attachment point, I'll say, what do we have to add using the equilibrium equations at the attachment point? And again, I'm looking at the sum of moments around the x-axis have to equal 0. The clockwise have to equal the counterclockwise. 10,000 clockwise, 6,000 counterclockwise. So you can see this has to be 4,000 Newton meters. Once I have that, if I'm looking at the shear stress in region 2, I know it's going to be the torque in region 2 times that maximum radius in 2, because I'm looking for where it's going to fail. And it's again going to fail on this outside circumference in this view, outside circumference in that view, divided by the polar moment of inertia for that cross-sectional shape. Again, whatever this value comes out to be, you're going to compare it to the yield value for region 2. If this is greater than this, it's safe. If this is greater than this, it fails. And then finally, if you do the last one, in this case, what I'm going to do is come and it in region 3. And I'm going to then sketch the left-hand side. So this is the left-hand side. I then sketch in any given forces, moments, torques, couples. And hopefully you can see we have 10,000. 6,000. And finally 4,000. We have one attachment point, which is where the left-hand side would attach to the right-hand side. That's the only place we can have a place to add forces, moments, torques, couples for equilibrium. So you know the sum of moments around that x-axis have to equal to 0. The clockwise have to equal to counterclockwise. So we have 14,000 clockwise, 6,000 counterclockwise. So that has to be 8,000 Newton meters to keep that in equilibrium. If we then look what's going on for my shear stress in region 3, which again is anywhere in here, just to the right of that, just to the left of that. We know it's the torque in 3, which we just found here, times that maximum value for the radius of 3 divided by the polar moment of inertia for that cross-sectional shape. Again, we get this value, compare it to the yield material for 3. If this is greater than this, it's safe. If this is less than this, then it's unsafe. Now, I have always, just sort of the way I operate, I've always had you start from the wall because that's fixed, and then work your way across looking at safety. But there's no reason that you can't do it the other way. So for example, when I made this initial cut here, I went and did the left-hand side. Could I have looked at the right-hand side? And the answer is, since it's in equilibrium, of course I can. So if I go back and look, and I've cut it here, and now I'm going to do the right-hand side. So again, I've cut it anywhere just to the right of there, just to the left of there, and I've sketched the right-hand side. This is ultimately what would attach here to this left-hand side. Then I look to put in any given moments, forces, torques that I have, and I have one attachment point where this thing attaches to the left-hand side, and I know I can only add forces, moments, torques there. The summation of moments around the x-axis has to equal to 0. So this is a very simple one. I then go back and I'm going to use the exact same equation because I'm out to find the shear stress for section 3. If you notice, this torque is the same as this torque is the same as this torque. The radius is still that distance it takes you to get to the circumference, so you know that's where it's going to fail. And the polar moment of inertia is a function of the cross-sectional area. Every now and then you might do this just to make sure that this is correct. And you know you've done it correctly because if you take the left-hand side, free body diagram, marry it to the right-hand side and put it back together again so that you end up with our total free body diagram, notice that this exactly cancels out this, which is what you expect, because when you look at this free body diagram, there's nothing going on in here. Those have canceled each other out due to equilibrium when you put them back together again. So you could have started doing a cut here, looking at the right-hand side, doing a cut here, looking at the right-hand side, doing the cut here, looking at the right-hand side, and still came up with exactly the same answers that you did when we did it going the other way. The only thing I would advise you is when you do this, be consistent in the direction you're going, just so that you don't make any silly math mistakes. And if you want to do a quick check and balance, you could take the very last one, like we've done. You've already done the left-hand side, do a quickie on the right-hand side to see if you come up with a number that cancels each other out. Okay. If I had asked you in this, if I go back here and I have at the very end point Q, and I show it in this view here, it's point Q, I could ask you for this system as loaded with torque as you see it, what is the final location or rotation of point Q? We know it can only rotate clockwise, counterclockwise. We know that to do this, this is going to be the sum of T1, L1, excuse me, TI, LI, JI, GI, from I is equal to 1 to N, depending upon how many sections you have or what point you're looking for. This is the torque that you find in each section when you do the free body diagram that you've already plugged into here and here. L is the length of the section involved. J is the polar moment of inertia for that particular section. G is the modulus of rigidity for that particular material. The only thing you have to remember when you do all this, and I'm going to erase this very quick to go back up here. We know those are vector values. We know that when we calculate this, that answer is going to come out to be in radians. We need to correct that to be degrees, so we need to multiply this times 360 degrees. It's equal to 2 pi radians. Cancel, cancel, so our answer will be in degrees. Then the only thing we need to do is determine the rotation, whether it's clockwise or counterclockwise. And before, I have recommended that you just start at the end. You can do this any way that you want to. You start at the end and then you make yourself a little note as to rotation. So in this particular case, counterclockwise at the end is a negative, or counterclockwise rotation. Assign a plus or a minus at each section accordingly. So for example, this is what we've sketched. If we go back and we look at this first cut, this is what we had for our left-hand side for region 1. That being the case, when we come up here, we know this value is going to be 10,000 Newton meters, because that is what we have found from our free body diagram for region 1. But what is the sign? Are we going to use a plus or minus in Y? Anybody? You got a 50-50 chance. Which sign am I going to use in Y?
Positive.
It'd be counterclockwise, so it'd be negative because that's the
It
attachment.
would be negative, because we have said down here counterclockwise is negative, because that's the sort of legend that we've established for the end. So if it's counterclockwise in the cut, it's minus. If we looked at the next one, so this was 10,000 Newton meters. This was 6,000 Newton meters. What is it in the cut here? It is 4,000 Newton meters. So this value is 4,000 Newton meters. Is the sign I'm going to use for this positive or negative in Y?
It's also negative because it's in counterclockwise rotation.
Correct. It's also negative because it's counterclockwise. And just for consistency, if we do the last one, which we've already done here, this value is going to be 8,000. Remember, I've gone back to this left-hand side. And what sign are we going to put according to this one? And why? Again, it's negative because this is counterclockwise. Okay. So when you do this algebra to come up with the answer here in radians, you know that Q is going to have to move counterclockwise because each of these values are negative. So whatever you come up with your final answer in degrees, it's going to be a minus value. And we know minus is counterclockwise. Okay. Anything else you want to review for the exam on Wednesday? Again, it'll be in class. I'll either make it an hour and a half or 2 hours, depending upon when I finish it up today, because I sort of give it to myself, and then I give you 3 times the amount of time minimum to work it. So any other thing you'd like to review for nuclear material science exam number 2, which will be on Wednesday? Okay. I would like to move on now to reactor theory. Again, I haven't looked at all the quizzes that's come in, but would anybody like to work for the rest of us for extra credit your solution to reactor theory quiz number 9? No takers. Okay, no takers, right? Okay. Okay, I have a block of tantalum 181. And I'm putting that in a flux. And I'm telling you that flux is 2 times 10 to the 20th neutrons per square centimeter per second. I'm telling you that it is epithermal at 42 degrees C. If I look at some of the properties for target. I know that the number of atoms that we have is equal to 9 times 10 to the 19th atoms. I know its absorption cross-section for thermal is 21 barns. If I look at my desired product, we know that that is tantalum 182. We know that its absorption thermal is quite large. It is 8,200 barns. And we know that its half-life is 115 days. So I'm going to use this information. I'm going to use the equation that we have for neutron activation, which is what we're doing. Okay. We know for neutron activation that the number of atoms, desired atoms, created as a function of time, and this is N2, is equal to the flux involved, the number of atoms that we have of our target, times the absorption cross-section for that target, because we need to know these are the atoms, this is a probability of an absorption, this is the flux. This will tell you the probability or how many of those are going to be absorbed to become tantalum 182s. We're going to divide that by the effective decay constant, because this effective decay constant has to take into account absorption by tantalum 182 plus its natural decay times 1 minus e to the minus lambda 2t times t. We know that if we plot this, versus time, we know that the number of tantalum 182s has to start at 0 when we first apply the flux, and it's going to go up and look something like that. One other thing I didn't ask you, but I could have asked you, I could have said, write the complete reaction equation for this neutron activation. If I did that, we know that we have our tantalum 181. We're striking it with a neutron, which it's going to absorb. So it becomes we know that this is the desired isotope we're after. This is what we're out to collect with neutron activation. This is, and let me erase this bottom. This is our compound nucleus. And then, since it is radioactive, it is going to decay. And let's see, I have that handy. Looks like this decays with by a positron emission. So this is going to have to be 72, 182, which is hafnium. Okay. So this is what happens when we have our neutron activation. We create our tantalum, which is the desired target we're after. But we know it has a natural radioactive decay, and we know that it also absorbs neutrons out of the flux. Become tantalum 183. So this is lost due to its absorbing neutrons. It's also lost to its natural decay. I didn't ask you that, but just to fill in that, the rest of that. Okay.
So how did you determine that there's a positron portion of the decay?
I went in the chart of nuclides and I looked at the preferred method of decay for that particular isotope.
Okay, thank you.
Okay, let's go back to our problem. Okay. Looking at the equation that we had, okay, what do we know? We know the flux, which was 2 times 10 to the 20th neutrons per square centimeter per second. We know the number of original atoms that we had, which is 9 times 10 to the 19th atoms. If we look at the absorption cross-section for our tantalum 181, we know we have to adjust that because we have an epithermal flux, and I didn't write that down, but the temperature was 42 degrees C. To make that absolute, we have to add that to 273 degrees C. So this is 315 degrees K. We know we can adjust our absorption cross-section by taking the thermal value, multiplying it by the square root of pi divided by 2 times the square root of room temperature, which is 293, divided by our epithermal temperature, which is this. This value we said was 21 barns. So we take this value, we multiply it by 10 to the minus 24th to put it in the proper units. And this is going to go in right there. Now we have to look and see what's going on down here with our effective decay constant, and we know this is lambda 2, which is for our desired product, plus the flux times the adjusted cross-section for epithermal for that. We know that this is 0.693 divided by the half-life. The half-life is 115 days. Okay. So that takes care of this part. This again is going to be our same flux, which is 2 times 10 to the 20th neutrons per square centimeter per second. Now we have to look and adjust this value for A. If I do that, and I'm just going to go back up here and adjust this. This is, we're now looking for the adjusted for 2. So this is going to be the thermal adjusted there. This is the same, except this value is now 8,200 barns. So this is going to be times 8,200 times the square root of pi divided by 2 times the square root of 293 divided by 315 times 10 to the minus 14 to get it into the proper units for cancellation. The only thing we have left to do before we crank all our algebra is to make sure that our units are alike so that our final answer will come out to be in number of atoms. So the thing we have to correct for or look at is this is in seconds, this is in days, this is in seconds. When we go back to plug this into the equation, this is in days. So we either have to correct the seconds into days or the days into seconds. When I worked the problem, I chose to correct this to put everything in seconds so that the seconds would, into days so the days would cancel out. So let me just look at this one. I'm going to do the same thing down here. So we've got those set. If I look at the flux, this flux is neutrons per square centimeter per second. I know that there are 60 seconds in 1 minute. 1 minute, 60 minutes in 1 hour. And 24 hours in 1 day. Cancel, 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 cancel. So I'll get days here. And I'm going to correct for days here. I'm going to get days there, where I'm also going to correct here. So when I make that correction, and then I do all my algebra,
Professor, I have a question.
the final thing I have to do is this value is going to be this whole thing. This value is going to be this whole thing. And then the final thing I ask you for, what was that value after 220 days? So this T is 220 days. So when I go through this days and that day, everything will cancel out. And the final answer I got was 2.31 times 10 to the 18th atoms. Questions?
I have a quick question.
And again, you might get a variation on this depending upon how you rounded off your answers. Yes.
In where it shows 8,200 square root of pi over 2, yeah, right there. Why did you times that by 10 to the negative 14th?
No, 24th.
Oh, okay. All right. I thought you said 14th.
If you look at the value for absorption that you get in your book, and this is whether it's thermal or whether we adjust it for epithermal, the units that you have in the book are in barns. We need to correct that to put it in the correct units so that it will cancel out. And basically what it's doing is it's canceling out with the square centimeters that is in the flux. And we know that one barn is 1 times 10 to the minus 24th centimeter squared. So we have to make that correction from barns to centimeters squared in order to have the units cancel out in the flux. Any other questions? Okay, there's a lot of number crunching there. This was an unusual problem because usually when you're working, you're going to find out when you look at this effective decay constant that lambda 2 tends to be much, much greater than this. So effectively, lambda 2t becomes lambda 2 in most instances. This time, because of the large value of flux, and particularly because of the large cross-section, that wasn't the case. Then the final part for extra credit. Everybody finished with this so I can erase this? Okay. Okay, if we go back to our plot, we know that our plot looks something like this, and this plot is this equation shows is that line. In the question that we had, we said after our 220 days, we had this value that we just calculated. I'm not going to call that our point of interest. At this particular time, we said that the flux went to 0. And if you go back and look at this equation, and you let the flux go to 0, this becomes then just our regular old garden variety natural radioactive decay of our substance. So N2 is a function of time. It's going to be the number of them that we have when the flux went to 0, which is this number. Times e to the minus lambda 2t is 0.693 divided by our half-life, which was 115 days. And we let this thing go for another 100 days. This is going to go to 320 from time 0, but this is going to be times 100 days because that's where I'm asking you to go in this equation. It's a natural radioactive decay equation that looks like this. So this is the plot of this equation. So when I threw my numbers in here, I have the number of tantalum 182s at 100 days, because that's the point that we're interested in now. That was equal to 1.26 times 10 to the 18th atoms. Any questions on that?
It seems like a lot of us got times 10 to the 17th and not the 18th.
Okay, I can go back and check my powers of 10, and I'll look at yours when it comes in. But thank you for that. So we'll see if this is 10 to the 17th. Obviously, this answer is going to depend on this answer, which is going to depend on that answer that we cranked out before. David, was that your question? Anybody else have a question on this? Okay. I'd like to hopefully finish off the rest of chapter 8 lecture-wise today.
Professor Sherrod, I have a question.
Yep.
So for the equation that you just did, I think you wrote it in red. That's a different equation from the equation in black, correct?
Absolutely.
Okay. All right.
This is neutron activation. Okay. This tells us how we're producing our tantalum-182s based on the number of tantalum-181s we had to start with, looking at absorption cross-section, the flux that's involved, etc. But when we look at this, once the flux goes to 0, we go up here and we plug in 0. What does that tell us? That tells us we are not producing any additional. So if the flux goes to 0, no new tantalum-182s are created. Because the only way you can produce these is by neutron activation of tantalum-181. So whatever number you have at that point when the flux goes to 0, it is radioactive. Therefore, it is going to decay, and it's going to have a natural radioactive decay, which is this equation. And since this is the number you had when the flux went to 0, it's going to have this plot, which is this equation. Natural radioactive decay, neutron activation. That answer it, David?
Yes, thank you.
Okay. Any other questions on this? Okay. I'm going to go through probably 15 minutes to half an hour worth of stuff, then we'll take a break. Then we'll come back, hopefully finish up the chapter. And I do have a quiz. I'm going to give you a brief quiz that will be due by Wednesday. Okay. What we've looked at thus far is, I'm going to give you the quiz today, and it'll be due at the start of class on Wednesday. Okay. What we've looked at thus far is we have looked at neutron interactions. And we've looked at absorption cross-section, or the probability of an absorption. And we've talked about a little bit a scatter cross-section, which is the probability of a scatter. And then we've looked at this total together, which looks at the probability of a neutron interaction by scatter and absorption. And the only real examples we've looked at thus far is absorption, which we just did with neutron activation. We're also very interested in what goes on in scatter. And for right now, when we look at scatter, there are two types of scatter. There's elastic scatter, and then there's inelastic scatter. Inelastic scatter is a difficult math solution. So for right now, we're only going to be working with elastic scatters, okay? And for example, when you look in the back of the book and you're looking at values for scatter thermal or scatter epithermal, remember those are the last two columns in the tables in the back for isotope properties. Both of these assume an elastic scatter. So in order to understand and apply scatter, we need to go back and look at the laboratory system versus the center of mass system. If we have a neutron strike a target, we know that we can write this as a compound nucleus. And to envision what happens, we can look at it two different ways. We can look at it in a lab system, and that's the one I'm going to present first, and we've discussed this a little bit before. With the lab system, you sit in the room and observe the scatter. So in this particular case, the velocity of the target is 0. We're just going to let it sit there. The neutron velocity is coming in that direction. If we look at conservation of linear momentum, we know that's a vector quantity p, and it's equal to a mass times the velocity of whatever that mass is. For conservation of linear momentum, we know that the linear momentum on the left-hand side has to exactly equal the linear momentum on the right-hand side. So, if we look at what's happening to our compound nucleus, will the compound nucleus have a velocity? Get rid of that. Make that a little clearer. By the principle of conservation of linear momentum, if this is stationary and this has some velocity, when it strikes this to become the compound nucleus, it must have some velocity going in that direction to preserve the conservation of linear momentum. So yes, there is. And in this case, it's going to be going in that direction. When the scatter actually occurs, the target is going to go off in one direction. The neutron is going to get scattered down in a different direction. But when you add this vector quantity to this vector quantity, you're going to have a slight total vector going in that direction, which you expect, again, due to conservation of linear momentum. This has a slight linear momentum going in this direction. This is going in this direction, so this must also show in this direction. This angle of scatter we call psi. And psi is the angle of scatter in the lab system. So if you're sitting here in the classroom and you have our good old target sitting up here stationary, you'll see the neutron come in from the left, strike this, briefly create a compound nucleus which is slightly moving in this direction, and then if we have an elastic scatter, you'll see the target go off in that direction, the neutron that is scattered go down in this direction. That's the event for the lab system. As I mentioned to you before, this is easy to visualize, but it is very difficult to calculate. So the way they got around that was to take this same situation, but now put it in the center of mass system, which you'll see abbreviated as COM. In this particular case, the compound nucleus is our reference point. And has a velocity of 0. So in this particular case, the velocity of our compound nucleus is exactly 0. And for you to better visualize that, what I do is have you sit on the compound nucleus. Then if you turn to the left and you look at the target was initially stationary, but now as you look at it, it's going to be slightly going in that direction. If you look at the neutron that was coming towards the target, it is also going to be coming in that direction, but at a lesser value than here. Why? Because we know that we have to conserve linear momentum. Okay. So the linear momentum for our compound nucleus is going to be what? It's going to be 0 because we have the mass of our compound nucleus times its velocity, but that velocity we've said is 0. So in order to make this 0, the linear momentum on the left has to equal 0. The only way that can happen is the mass of the target times its velocity has to exactly balance and be reversed to the mass of the neutron times its velocity. If we then look at the right-hand side, if the target is scattered off in that direction, we know our neutron has to be scattered in that direction, because when you look at the linear momentum of the target, you add to it the linear momentum, and again, on the right-hand side, we know that has to equal 0. So now the mass of the target times its velocity has to exactly equal the mass of the neutron times its velocity. So this vector quantity has to exactly balance out that vector quantity, because the total linear momentum on the right has to equal to 0, which is the linear momentum for the compound nucleus, which is the linear momentum on the right. This particular angle of scatter is called theta, and theta is the angle of scatter in the center of mass system. If we look at what is happening here, if we look at scatter in the center of mass, there's an equal probability of a scatter to any angle theta. So when this scatter occurs, the target could have gone this way, the neutron could have gone that way. Just as likely, the target could have gone this way, the neutron could have gone that way. So there's an equal probability of any direction. We call it isotropic scattering, because it has an equal opportunity of going in each direction. If we went back and looked at scatter in the lab system, if you remember, the target went off like this, the neutron went down like this. If you look at all the possibilities of scatter in the lab system, you're going to see that the neutron has a slight probability of going in that direction. We call this a forward scatter rather than an isentropic scatter. And why is that? Because when you're sitting here in the room, this is stationary, this is moving in this direction, the compound nucleus has to be moving slightly in that direction. When this thing scatters, if you look at all the possibility of these, because of conservation of linear momentum, the neutron has to be moving slightly to the right when you look at all the possibilities, just because of that conservation of linear momentum. So if you're sitting here, in general, you're going to see that neutron go somewhere to the right. Could it also go to the left? Yes. But again, those vector quantities have to balance out to make sure your conservation of linear momentum is 0. Okay. So, one final thing, and then we'll take a little break. And this presentation is also shown in your book on page 230. If you look at the average value of scatter in the laboratory system, psi, you look at the angle of scatter in the center of mass system, you can connect these two, and it's going to be the velocity of the compound nucleus. So this is the angle of scatter for our scattered neutron in the lab system. This is the scatter in the center of mass system, and you can connect those with the velocity of the compound nucleus. When we come back, we're going to develop an equation for developing or analyzing the angle of scatter and the energy loss in a scatter for an elastic scatter. And for the rest of the time, we're only going to use the center of mass system because that's the easier one to calculate. Any quick questions on what we've done? Okay, I'd like you to take a 10-minute break. According to my watch, I'll have you back here at 5 of. When we come back at 5 of, I'm going to start into establishing directions of scatter, energies associated with those scatters, and then finish up the rest of this chapter this afternoon. Give you a very easy quiz to do that will be due at the start of class on Wednesday. Any quick questions on what I've done so far? Okay, I'll see you back here in 10 minutes. Okay. We've now gone through establishing center of mass system scatter, laboratory system scatter. We know that they're all elastic scatters. Your book spends about 3 pages developing an equation for again, this was done in the center of mass system viewpoint. And if we look at, let me start over again here. If we have a neutron coming in this direction, and this is our target, if I draw a vertical line through this, and then we have a line the other way for the direction of travel, if we look at this in the center of mass system scatter, this is 0, this is 90 degrees, 180 degrees, 270 degrees. If our neutron strikes our target, undergoes an elastic scatter, and ends up traveling in this direction, so that the angle of scatter is 0 compared to its initial direction, this results a minimum of energy transfer. And again, why do we have scatter? When neutrons are created, they're very energetic. We need to have them lose energy from wherever they are and get down to the thermal energy range. So scatter used to reduce neutron velocities or energies to thermal values, and that thermal value can hopefully cause a fission. So if it's scattered directly ahead, the angle of scatter is 0, there's a minimum energy transfer. Hopefully you can see if it gets scattered exactly backwards at 180 degrees, this 180 degree scatter produces a maximum kinetic energy loss. So that's when theta is equal to 180 degrees. If we look at anything that is scattered anywhere from plus 90 down to 270, we call this a forward scatter. If you have anything that's scattered In this direction, this is called a backscatter. I don't know how many of you, when you get your Nuclear News magazine, if you looked just inside the back cover, so if you take the thing all the way to the back and open it up so you're looking inside the back cover, there's the back cover, and then the first page inside, if you look on that, there are letters to the editor about anything and everything to do with nuclear society. It could be technical, it could be social, it could be anything. And they call this page backscatter because that gives the readers a chance to get back to the editors of the magazine. So if you've noticed that, that's where that term came from. Okay. So we have a forward scatter, anything from the original direction to plus 90 to 270, this 180-degree arc. Anything going the other way is a backscatter. Your book has developed an equation, center of mass system, to look at any energy loss for any angle of scatter. So again, they took about 2 pages to develop this equation for you. And what this equation turns out to be is kinetic energy out divided by kinetic energy in is equal to A squared, and you want to follow this. This is on page 230. It's A squared plus 2A cosine of theta plus 1 divided by quantity A plus 1 squared. Okay. And this is a relationship between the kinetic energy in to a kinetic energy out based on the angle of elastic scatter. So we were just working with tantalum 181. Okay. So if I told you a 2 MeV neutron struck a stationary Ta-181 atom, what is its energy if it scattered 80 degrees? In order to utilize this, our energy in is 2 MeV. A for our tantalum 181 is 181 squared plus 2 times 181 times the cosine of the angle scatter, which is 80 degrees, plus 1 divided by 181 plus 1 squared. So I do this algebra, multiply times this, I'm going to have that kinetic energy out. So hopefully somebody has their calculator and you're going to tell me what that kinetic energy out is, what that value is. So what'd you get for an answer? 1.796, okay? So this kinetic energy out is 1.976. Okay? Everybody get that? Hopefully everybody's using your calculator on this. Okay? Then let's say I tell you that our scattered neutron now strikes our tantalium again and has a 225-degree scatter, elastic scatter. I want to know what is the new kinetic energy and direction of travel. Okay. So we're going to go back and use this same equation that we had before, except now the kinetic energy in is 1.976 MeV. We're looking for what comes out. This is the same, this is the same, this is the same, but my theta is now 225 degrees. So while you're working on that, if we look and see what is happening to our neutron, initially it experienced a scatter of, it was coming in this direction at this energy, and it had an 80-degree scatter. So we know that if this is 0 degrees, it had a forward scatter. and it went in this direction, where this angle was 80 degrees. If we now superimpose our grid, by grid I mean this axis, if we transpose it onto here, so this is my angle of travel, it's now going to scatter 225 degrees, so 90, 180, 225. So it's scattered down in that direction. So the final direction of travel is my initial 80 plus my 225, which is 305 degrees from where it originally came in. I actually need to draw this a little bit over to get it to be 305 degrees. So we know that's the direction of travel. Has anybody done the math here to see what my energy out is? Again, we expect this value to drop because it is an elastic scatter. Anybody get that number yet?
For clarity, Professor Sherrard, the angle that we put in for the cosine, is that 305 or do we put in 225?
You're putting in the one scatter, which was at 225 degrees.
Okay.
The 305 is the final angle of travel from when it initially came in. Initially came in, got scattered 80 degrees. That travel got scattered again 225 degrees. So compared to its initial direction of travel, this thing is now traveling at 305 degrees. So it's going somewhere down like that. But this value is the 225 cosine. Anybody get a value? This is a squared plus 2a times the cosine of theta, and then plus 1. I got 1.95 MeV. Anybody else get that? If you didn't get that, let me know what you did get. Anybody get an answer?
I got 1.98.
Okay, if you're using this value to start with, it cannot increase in value because that would defy conservation of energy. So whatever you have, the most it could be is its same value, And how would it be if you came up with, if you started out with 1.976 going in, and what you had coming out was 1.976, what kind of scatter would you have and at what angle?
Okay, I mistakenly
Forward 0.
but yeah.
If you got exactly the same value, that would mean your theta was 0, and it had a perfect scatter ahead, which it did not lose any energy. So other than the unique case of it scattered directly ahead, this value will always be less than the value coming in. Because again, we're using scattering to get the energy of our neutron down to thermal energy so it can cause a thermal fission. Everybody get that? That ballpark answer? Okay?
What?
So
Can you repeat what value you got, what your answer was, please?
I got 1.95.
Okay, thank you.
That's what I was asking if anybody else got that. Okay. Let's go look at another version of this, since it's getting a little messy. Let's have a 10 keV neutron. Have 2 elastic scatters in, let's just pick something out of the back of the book. Cobalt 59. Okay. And those scatters are 115 degrees and then 292 degrees. What I want to know is, what is the final kinetic energy, and what is the final direction of travel? If we look at the travel first, a neutron is initially coming in at this angle, 0. It's scattered 115 degrees, so here is 90. So it has a backscatter where it gets scattered back 115 degrees. And then if I superimpose this grid again, where this direction is 0, and it gets scattered 292 degrees, so 90, 180, 270. It's going to be scattered back around something like this, so it's going in that direction. We know, because it's center of mass system, that we can add the 2 values. Okay. Subtract from that 360. So this is now scattered what? 47 degrees. So neutron came in, experienced 115 degree scatter, then experienced a 292 degree scatter, so that its final direction of travel is 47 degrees from where it was originally coming in. Okay, that's fairly easy to do. Now we go back and look at the kinetic energy. After each scatter, this is a squared plus 2a cosine of theta, put parentheses so you don't mess that up, plus 1, divided by a plus 1 squared. So in the first case, we had a 10 keV neutron coming in. Our cobalt's mass is 59. Let me change colors here. So that's the atomic mass squared plus 2 times 59 times cosine of 115 degrees. All of that plus 1, and then this whole thing divided by a, which is 59, plus 1 squared, which is 60 squared. So if I do this algebra, let me know what you get for the kinetic energy after 1 scatter. And we know it's going to have to be less than that because it was not a perfect forward scatter. .5. That's what one person got for me. Does anybody else get that? Okay. So after that first scatter, we know that our scattered neutron is going in this direction, which is 115 degrees, and it's going at this energy. When we do the second scatter, we're going to use this same equation again, except now the energy in is this. This is the same, this is the same, this is the same, but now our cosine is of 292. This is the same, this is the same, and we need to see what that final value is. So again, when you do that algebra, with this now being the cosine of 292, and again, we expect this value to decrease because we've had an elastic scatter that was not a perfect forward scatter. Anybody get an answer yet? That's what one person got. Anybody else get that or something close to it? Okay, somebody else got 8.8. Somebody just said something that bounced off the screen. Did you put it back? I didn't get either one of those. I got 9.0. So I need to see what anybody else is getting so we can try and figure out what's happening here, what's going wrong. Okay. Depending on how you round off, it could be that. Okay. The other thing I wanted to show you on this, we can determine the final travel center of mass system by merely adding the angles of scatter. And it's all in reference to the initial coming in. If you look at this equation that we've been working with, when you have an initial scatter, you get a value, but this value then becomes what's coming in. So if you look at going through multiple scatters, the final kinetic energy out after, let's say, 3 scatters, it's going to be the kinetic energy in times a squared plus 2a cosine of theta plus 1 divided by a plus 1 squared. Where this is the first angle of scatter times a squared plus 2a cosine of theta plus 1 divided by a plus 1, where this is the second angle of scatter times a squared plus 2a cosine of theta plus 1 over a plus 1 squared, where this is the third angle. So whatever you have your energy coming in, look to see what the mass is of your target. Look to see the angle of scatter. If you have three separate scatters, you do this calculation, multiply it times this calculation, multiply it times this calculation, times the original energy in, and then you have the final energy out after our three elastic scatters. And you know that final angle direction for scatter. Because it's the center of mass system, you just add the three angles of scatter. So you have the ability to find the energy out compared to the energy in for a perfect elastic scatter for any target material versus any energy coming in from a neutron after any number of scatters. Some other things to note, if we go back to our equation, if theta is 180 degrees, which is a perfect backscatter, so the perfect backscatter means the maximum energy lost in one scatter. If for theta I put in 180 degrees, this equation becomes K out over K in is equal to, on the top, if you factor, this is being A minus 1 squared over A plus 1 quantity squared. So, we call this term alpha, and you put a subscript of whatever the isotope is that you were doing. For example, we were just doing cobalt. So if you want to see what that value would be for cobalt, sixty minus 1 quantity squared over 60 plus 1 quantity squared. I think that was the cobalt I was using. Hang on a second. Yes, I was using 59. So this is 58 squared divided by 60 squared. So that value comes out to be 0.9344. Okay? Everybody get that? So for a perfect backscatter, in cobalt 59, we can only lose 6.56% of the energy, because this is the energy remaining. So if we look at cobalt and we have one perfect backscatter, the most energy you can lose is only 6.58%. Excuse me, 56%. So that's not very good. So you'll find out that the larger mass isotopes and atoms only reduce the energy a little bit. Notice that this energy loss percentage is independent upon what the energy is in or out. So if this is 2 MeV, it will tell you what it will be coming out. If this is 1 MeV, it will tell you what it is coming out. Let's look at a lower value. Let's look at...
Professor, how did you get that 6.56% again?
I took 100% and minus this. In other words, this is the energy left in a percentage after one perfect backscatter. So this is the energy remaining. So the energy that was lost, which would be 0.0656. This is the energy lost. And I just converted that to 1%. Okay. So let's look at something that has a low mass. And again, we always designate the fact that we're going to look at this optimum backscatter amount. Let's look at it for hydrogen. Okay. So it's going to be A minus 1 squared over A plus 1 squared. Mass of hydrogen is 1, so 1 minus 1 squared over 1 plus 1 minus 1. What's that value? That's right, 0. So this tells me if I have one perfect backscatter of a neutron with hydrogen, there is 0% energy left, so I can lose all kinetic energy with one perfect backscatter in hydrogen. Notice this doesn't have anything to do with what's coming in. So this could be a 2 MeV neutron that has just been created with thermal fission. It could be a neutron that is at, let's say, 150 keV that's scattered around a while. If I have a perfect backscatter, I can lose all my energy. That's great. Because again, we want to get from some energetic value down 0 is effectively thermal. Of course, the problem is, since this is isotropic, the fact that we're going to get the occasional perfect backscatter, most of the time, it's going to be scattered at some angle, so you're not going to lose the entire amount. That's why you tend to use lower mass materials to be moderators in a reactor, because we know that the lower mass materials can lose a larger amount of the energy with a perfect, a last backscatter, particularly backscatters. So that's why your good moderators are very low mass materials. And we always use this designation alpha for any particular material to see how effective it is with a perfect backscatter to determine the amount of energy that we have lost or available after a perfect backscatter. And again, we do use this for anything, so if you want to look at it, say carbon, that value is at 0.716. So this is the percent energy remaining. So one perfect in carbon removes 28.4% of energy. So that's pretty good, but it's not as good as hydrogen. Okay. The other topic, so we'll go over today to close this out. And any questions on this? How you can find kinetic energy, direction of travel from one or more elastic scatters? And how do you develop or define this alpha quantity for any material? Okay. The final thing I want to go over is and if you want to follow this is on page 232. And there's something called rhythmic energy decrement or decrease. And this is defined by psi, what in the nuclear industry we call squiggling. And it is defined by the average loss they keep the shift terms of this. So it's the average energy on 1 megawatt, and I do not know how that term came to be. I tried to find that out. I chatted with some other folks. This is even back when I was going to grad school as to where the term came from. I haven't been able to find it out. I think it's they just random and it's a week later. That moves like squiggle, so they call it that. If you go to the
energy, what is our DE? What's the word next energy?
decrement. So it's looking at per energy collision elasticity. It's looking at the energy loss, and then it's averaging these over all possible collisions. Again, I'm not sure how they came up with this term, but they did. When you look at putting in equations for energy, again, this is based on energy. You substitute this back in, you'll find that squiggle can be reduced to, this is equation 8.56. So, squiggling for any material, now typically use a subscript. So if I was to do this for, let's say, carbon, squiggle for carbon, I would put in, wherever I see an A, I would put in a 12. And this is the logarithm of the absolute value. In this case, it would be 11 divided by 13. So, if you substitute it in A, whatever material it is, you can calculate squiggle for that particular material. And this is a true value that exists all the time. If A is greater than or equal to 6, this equation reduces to 8.57, which is 2 divided by A plus 2/3. So if I was to find out the squiggle for carbon, I could get an absolute value, true value of this. I would get the very good x approximation by using this, which would be 2 over 12 plus 2/3, or 2 divided by 12.667, for whatever that is. That would give you the average energy decrement for carbon. It looks at all the scatters that can occur in carbon. They're all plastic. It averages them looking at a logarithmic difference to come out with that value. And then, if you apply that back to the loss of energies, you can come up with an expression n is equal to the logarithm of energy n divided by energy count divided by squiggle, and that will give you, for any material, don't use carbon again, this is the average number of elastic scatters to go from energy in to energy out. So, let's say I have a neutron at 1 MeV energy. And I to make this neutron have thermal energy. This is using carbon. So if I come in here, my energy in is 1 MeV. I want to get it down to thermal 0.0253 eV. So I may make like units, I don't know, I was 10 to the 6 eV. Squiggle is this guy is 2 divided by 12.667. So if I take this, take the natural log of it, divide by this, I will have that average number of scatters. It takes the carbon to take a 1 MeV and make it carbon. So let me know what you got that. E out is thermal is 0.0253 eV. So anybody got a number on one more? Convert 180 to just MeV divided by thermal energy. Take the natural log of that, and then divide it by squiggle or carbon. I got 110.79. Anybody else get that? Since you cannot have a fraction of the scatter, I will round that up to 111. So using the concepts of wiggle, natural logarithm energy decrement, for carbon as a non-operator, with the last scatters, to take a 1 MeV neutron to reduce the thermal energy, takes, on the average, 111 scatters. So each time I have a scatter, the energy in your neutron reduces a little bit. X-ray reduces a little bit more. So that I have 111 energy slide down to thermal energy, so that neutron calls a next thermal fission. That answer says, after each one of the scatters at that energy level, that neutron can either be absorbed by something else because it's lost, or it can be reacted. So you want to reduce the cell number as much as you can, and that goes to selecting a Did everybody get that right? You want we can try it out very quick before we do quiz. I like everybody work on this. Okay. Have magnesium. I 200 kV and I want to renew that to 50 kV. So I don't know how many scatters I like scatters will they take it down there. I know again that's going to be of 200 kV by 50 kV. Energy out divided by squiggle. But what is squiggle? Squiggle is sensitivity greater than 6. A is 1.4 plus 0.67. 2 divided by 4.667. This is 2 divided by 24.667. So if I do that number, I have that number. And let's say that goes over 80. And I have about 17.1.
Yeah, so that equation that you just did is if the neutron in the element is greater than 6.
Say that again.
So for what you did is that if the neutron in the element is greater than 6.
What? I'm not really sure what question was. Because I haven't had a problem with these ones on this end. So we have a 200 kV neutron and it's like out of magnesium. I want to know how many neutrons a wax scatters is 8. Get that down to energy of 50 kV. From my equation. So it's not all 20 kV, but 50 kV goes against the allowance. And then I have to find wiggle or magnesium. I don't know what it says that magnesium has a great resistance. I can use this expression. So it's 2 divided by A plus 2/3, or 2 divided by 24 plus 6/7. I don't know all that down here. I got this to be an average number of equations. Which can have partial solutions to always mess up this with the 18 equations. Anybody else get that? Okay, everybody's doing this. I got that as well. Okay, thank you. Okay. Any more questions? diagram. Okay, that's just simply quiz that we do on start class on Wednesday. Okay. You finish to make sure I got it. Okay. Everybody got it? So you read it. Yes. Okay. So, 10 points. Have a 1 in the do strikes a lot of medium, 1.15. It undergoes 4 scatters. First 165 degrees, then 122 degrees, and 83 degrees, and then 308 degrees. What I want to know is what is the final direction of travel? What is the final energy of our neutron after those scatters? I want to know then what is the alpha value of helium, and then how many plastic scatters in helium would it take to reduce the neutron's energy from 1 MeV to thermal. That's synthetic quiz. And then for extra credit, I'm going to have to dig around in your chapter for this. For our helium 115, what is the average value of scattering in the laboratory system? That has to do with the start of class on Wednesday. Again, we'll have that to start with. I'll wrap up anything you have for chapter 8 for neutron interactions. Then I'll give you your exam in class if you do by 3:15 to take off first glance. I'll let those. I rate them over the weekend. I'll have that to you on Monday with the solution. Email that out to you. Again, I'm trying to put out our statement that you need to give us a receipt help. They take the exam. I'm always going to do that for exams. Next week, I'm going to start lecturing for Reactor Theory. I'm going to start on chapter 9, which is steady-state reactor. And this is definitely not math-wise. And then for nuclear science, we're going to start on the topic of nuclear bending. Temperature torsion before, now we have temperature bending. Let's start lecturing on both of those. This is all the theory that gives you on Wednesday. Any questions you need on anything? Again, when you're reimbursed for your ANS dues, just let me know that. We'll renegotiate the stipend check. Otherwise, I'll be around about 7 o'clock